Chemist Drive videos, Coulombs Law. Now, as it states here, Coulombs Law just says that the force of a charged object on another charged object is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. So, what does that actually mean? In actual English, what that's saying is that we've got two items up here that are charged particles. This could be protons, charges of 1, so it could be protons with a positive charge and electrons with a negative charge, divided by the distance between them, okay, in a squared amount. Now, it also has a constant here, but since we're talking the same for everything, we can just kind of ignore this, because in chemistry you're never going to have to figure out what the actual charge or amount of this force out here is. You're just going to have to compare one to another to determine how one would come apart. Which one's going to hold one stronger? Which one's going to be this? So we look at this charge of one particle and the charge of another particle, and then the distance between them to help us determine that. Now here's another example, and this is what we're talking about, the charges. So this could be if I was talking about a single atom, okay? If we were just talking about the atom and we were looking at something like helium. Helium has 2 protons, okay? Its atomic number is 4 because it has 2 neutrons, but its protons would be 2 positives. Since it is not charged, it then has 2 negatives, okay? And that would be the charged particle of this, 2 plus, times 2 minus, divided by the distance. If we were to look at this, the distance from these protons in here to these electrons that are out here. And that distance that's in here is what we're looking at in this area here to determine the force of the pull into that proton on this outside electron. Now, if we're just looking at a periodic table and a single atom, then the biggest thing this has to deal with is something called ionization energy. And that is the amount of energy it takes to remove one of these electrons to become a charged particle or become an ion. Remember, all metals lose electrons and become cations, okay? All metals. Non-metals do not lose electrons, they gain electrons, and then they would become an anion. But that would be non-metals. So what we're looking at here mostly is, as I said, this ionization energy. How much energy is it going to require to pull one of these electrons off? When you're looking at the periodic table, this is how we determine. Remember, everything in column 1 is going to form a 1 plus charge. So that means it's going to lose 1 electron. Everything in column 2, okay, is going to form a 2 plus charge. So 2 of these electrons then have to be removed for that to form this 2 plus charge. This also ties into what we're going to study in another video here called electron configuration, and you'll be able to figure out why certain elements lose a certain amount of electrons, okay? But it all has to go back to Coulombs Law, okay? That determines why certain electrons are lost and certain ones are not, depending on this force. That this force here is pulling. See, the force is pulling on these two because the distance is so small, and it's less on these out here. So that's why the outer ones, which is also known as the valence shell, are the electrons that are lost first, because of Coulombs law, that force is going to be less out here than it is inside on these interior ones. Now, if we're talking about chemical bonding, we're basically talking about ionic bonding, okay? So we're talking about ionic bonding because remember, ionic bonding is going to be a metal plus a non-metal. So you would have a metal plus a non-metal is what an ionic bond is. That forms a crystal, okay? A crystal structure. That crystal structure is what we call a lattice, okay? And that energy that takes to go from this crystal down here to totally fall apart to go into gaseous atoms, that's why it shows here these gaseous atoms, okay, is the amount of energy we're talking about. That energy being pulled and holding it together is determined by Coulombs law. Now this here could be sodium and chloride. So this could be a salt crystal of sodium chloride, and we would have a +1 charge and a -1 charge, and then determining by the distance that those are held together would tell me how much lattice energy that is. When you're taking tests on this, usually you have to compare one to another. Normally that would look some type of a chart like this, whereas here is the lattice energy for each one of these, and it has to do with the distance and the charge. Let's take a look at these two right here, okay? Why does lithium fluoride require 1,030 kilojoules per mole to form a gas, yet lithium chloride is only 834, okay? So what that means is that if we have lithium has a +1 charge, fluorine has a -1 charge, okay? So over here, lithium still has a +1 charge. And over here, we're going to have chlorine, which is a -1 charge. So the Q1 times Q2 is the same for both of them. However, when we look at the periodic table, we can determine that fluorine, way up in the corner, is a very, very small atom. Chlorine has a whole nother energy level around it and is much larger. So the distance between the protons, and the electrons on those outer deals, okay, between those two atoms, the internal deal of those atoms, okay, these are going to be tighter, closer. The closer they are, just as it says, the distance, okay, inversely proportional to the distance, is going to form a higher bond, a stronger bond than this one. Thus, it's going to take more energy to break apart something that is really tight and held together. And it's going to take less energy if we get all the way down here to, let's look at potassium chloride. Potassium still has a +1. Chloride still has a -1. The charges are the same, but potassium is much larger. And chlorine is still the same size as the one up in here. They're at the same size, but now those two nucleuses are much further apart. Thus, it's going to take much less energy to break those atoms apart. When we get over into here, these compounds, well, magnesium has a 2+. So this would be 2+, and chlorine would be a -1. So now you're starting to see I've got a stronger charge. So besides the distance that we talked about of everything in column 1, we get into column 2, we now start to talk about increasing the amount of charge. Now I've got the charge difference and the distance up here. Thus it's going to require more energy to pull those things apart. Now, Coulombs law and the force that it creates is one of the main concepts of college chemistry and AP chemistry. So you need to review this as often as you possibly have to just to get a good understanding of this law. Remember, I don't ever believe you're going to have to actually calculate out the amount of force. You may have to at upper level college, but at high school and if you're taking the AP exam, that's not going to be required. However, you are going to have to understand the charges and that inversely proportional distance and how that relates to each other in just a single atom or in a compound, ionic compound of somewhat, and the lattice energy. So remember, any questions you have, make sure that you bring them in and ask, and never, ever, 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 ever give up.